Good afternoon, I'm Umang, and this is joint work with Dilip Kini and Mahesh Vishwanathan at UIUC. And the title of the talk, as you can see, is What Happens After the First Race? Or an equally appropriate title would have been, What if I told you that your race detector is not sound? I'll come back to this in a moment. Let's first talk about concurrent programs. This whole session is about those. Concurrent programs are very popular everywhere, but at the same time, they're also very hard to write, very hard to reason about. And data races are one of the common problems for programming errors in such programs. Talking about data races, I'm going to be talking about data race detection in a dynamic fashion, wherein you observe an execution and then try to infer the presence of data races. Two popular techniques in this school of techniques are lock-set-based violations, and the other is based on happens before. Lock-set-based violation essentially is the idea that if you have two events that are protected by the same lock, then they cannot be concurrent. Happens before, on the other hand, is a partial order, first proposed by Lamport, that relies on some dependencies. Lock-set-based detection techniques, are unsound in the sense that they raise false positives. Now, this is not an ideal thing to have for a bug detector. On the other hand, happens before based techniques are sound or supposedly sound. They're not supposed to raise any false alarms. With this in mind, we tried some of the tools out there for that implement happens before based race detection, and these are some of the most common tools out there. Thread Sanitizer was initially built by Google. Now it's officially shipped with LLVM. Hellgrind and DRD are shipped with Valgrind. And FastTrack is an academic tool that sort of proposed some optimizations on the top of the usual vector clock algorithm. We tried a very simple example, a very simple program on Thread Sanitizer, and it so turns out that Thread Sanitizer is actually unsound. It reports false positives. And this is not just it's not peculiar to Thread Sanitizer, but also to the other three race detectors. And that's why when I said this is an appropriate title, this is what I meant. So while happens before guarantees soundness, tools that implement happens before are not sound. So let's dig deeper and let's take a look at this example. So I have a program here. It's a multi-threaded program with two threads, T1 and T2. In the first thread, you write to y x plus 5. In the second thread, there's a conditional that depends on the value of y. And initially, you start with x and y both 0. So one execution of this program is here. It has 4 events. So I'm assuming sequential consistency. So it's a sequence of events. The first 2 events are basically the read of x and then the write to y. And then the context switches to T2, and then you read y, so you would read 5, and then you would enter the then branch, and you would write to x. So each of these tools correctly report the race on y. But they also say that there is a race on x. But that's not true. So that's because if you try to schedule the read x and the write x concurrently, something like this, you would have to also push the read on y above here somewhere. And if that happens, then this read of y will not see the value 5. Because that write of y over here in thread 1 will actually happen later. And if that happens, this branch here will not evaluate to true, and you will actually end up going here, in which case you would not even execute write of x. So this race on read of x and write of x is not really a race. It's a false positive. Yeah. So let's look at the actual guarantee that happens before gives. So it, in fact, is the following. If you have an execution, so sigma is an execution, and if that execution has a conflicting pair of events, by conflicting I mean there's a write-write or a read-write on the same memory location but in different threads. And that pair of events is unordered by HB. Then the execution has a data race. In fact, it is not the following. HB soundness guarantee doesn't say that any 2 conflicting pair of events that are unordered by HB are a data race. So HB really guarantees the feasibility of one race. That's the first race it detects. At this point, one might ask, why even care about multiple races? And why not just discover a race, fix it, run your tool again, etc. Well, the first race that you might observe might not really be a race, possibly because you missed a synchronization. You did not instrument some external library. So the tool that you're running doesn't know this, but the developer knows this, and he doesn't want to fix the first race. He's interested in further races. Vector clock algorithms are costly. They have a lot of overhead, so you don't want to rerun your analysis again and again. Finally, it might be difficult to reproduce the later races because of inherent non-determinism, and also because the test inputs that you started out with might be unavailable. So with this in mind, let's try to fix the soundness guarantee of HB. And the first thing that is the most naive approach that comes to mind is probably use a SAT solver. So what I mean here is that if you have a race pair that is reported by HB, you encode the feasibility of this race pair as a Boolean satisfied with problem, and then you ask a SAT solver to check for feasibility. But then, as one can guess, this is not likely to scale. These executions have millions or possibly billions of events, and if you have such a huge SAT formula, that's not going to work. So the tools that actually do such a thing resort to what is called windowing, or basically restricting their analysis to trace segments in your trace. But if you do that, you can miss out on races that are across windows and are easy to detect. So the second approach, which is also naive in the sense, and it is the following approach. So as you're running your race detector and you encounter a race, you report that race, and then you force an order between the two race events and then move forward. So one can show that this approach is sound in the sense that the later on races that you discover are indeed true races, but then you can miss races if you do that. So here is an example of why that's true. Again, a simple example here. This is a program with 2 threads and an execution of this program. So as you can see over here, both y and x are in race. So this execution, if you look at, you will first encounter this race, and you'll report this race, and then if you order this race, what will happen is that thread order and transitivity will tell you that the read x and the write x are ordered. So at the time, so when you come to write x, you will not detect it as a race, but that's really a race. So this naive approach is also going to not work. At this point, let's talk about the approach in our paper. It's this new partial order called SHB, or schedulable happens before. And SHB is nice in the following sense. It is sound. Any races that it reports are true races. It is complete. It does not miss any HB races. That is, it does not miss any race that HB reports and is a true race. It is efficient. It is as efficient as HB. There is a simple linear time vector clock algorithm for analyzing races using SHB. And lastly, there is the algorithm for detecting SHB races is very similar to that of HB, and existing race detection tools can be easily modified to incorporate SHB. So with this in mind, let's formalize things a bit. As you might have noticed, I was arguing about some reorderings of traces and checking whether those reorderings are feasible or not. So this is defined formally as follows. Let's say I have a trace sigma. Then this other trace rho is a correct reordering of sigma if, number one, rho preserves the intra-thread ordering. So I'm assuming sequential consistency here. This is just a fancier way of saying that. It says that if you look at any thread, then the projection of rho onto that thread is the same as that of on sigma modulo prefixes. And the second thing that we want to ensure is that our control flow is preserved, which is every read in rho sees the same value as in sigma. And one conservative way to approximate that is by saying that every read event in rho sees the same last write event as in sigma. So the motivation for looking at this definition is that you do not have access to the program, but you want to make inferences based on the execution. And any program that executes sigma will also execute any correct reordering of sigma. So here is an example of a trace. If I remove the last event, what you get is also correct reordering of the original trace. In fact, if you try to reorder this event up there between 2 and 3, that's also going to give you a correct reordering, because none of the read writes are, the order of read writes on the same variable is not going to change, and thread-wise prefixes are preserved. But if you try to push this right way up there, that's not going to give you a correct reordering. So let's now define data races. If you have a trace sigma, and if you have a pair of events E1, E2 inside the trace, then E1, E2 is a data race if you can find, so E1, E2 is a conflicting pair of events. E1, E2 is a data race if there is a correct reordering of sigma, let's call that sigma prime, such that inside sigma prime, E1, E2 are consecutive. So this is an example again. This race, or this pair of events is indeed a race because this reordering is a correct reordering and it places the two events close to each other. Whereas if you look at this pair of events, that's not a data race, because if I try to schedule them next to each other, I will change the order of write x and read x. So that's not a data race. With this in mind, let's define happens before. Happens before is this partial order on the events in an observed trace, which orders events inside a given thread, so intra-thread ordering. And it also orders critical sections by ordering the release of the first critical section before they acquire. SHB is HB with some more constraints. It says you also add the ordering between a read and the last write before that read. So this might look simple and intuitive, but note that we are not adding these kind of edges. We're not saying that a read should be ordered before later writes, and we're not saying that a write should be, all writes should be ordered. So these are not the constraints that we require. So SHB, as you can see, is a slight modification of HB, and the guarantee that SHB gives is the following. So if you have a pair of conflicting events that was detected as a race by HB, then it is a real race if and only if there is no event E3 that is SHB after E1 but SHB before E2. So let's contrast this with the soundness guarantee of HB. HB only talks about the existence of one race, whereas SHB characterizes every pair of events. So here is an example that gives you the difference between HB and SHB. The write Z and the write Z here are not ordered by HB, and HB in fact says that's a data race. But SHB on the other hand adds these constraints, and as you can see, this read X is SHB after this write Z, and this read X is also SHB before this write Z, and therefore SHB based race detection will not declare this as a race. So the algorithm for SHB is similar to that of HB. It's a vector clock algorithm, and the idea is to assign timestamps to each event such that these timestamps mimic the SHB partial order. And the only change beyond HB is that you add an additional vector clock for each memory location, and the purpose of this vector clock is to track the timestamp of the last write event. Complexity-wise, it's really the same as HB in the worst case, both in time and space. And the very little change that you want to make to HB is this addition of this extra clock. Our tool that implements HB, SHB, and this naive force ordering business is implemented in Java, and it's available on GitHub. We use traces that are extracted by this commercial tool called RV-predict, and we also do some sort of optimizations for this vector clock algorithm. So let's look at some numbers. As you can see, the examples that we have are sort of standard about 18 of them pretty comprehensive. The number of events in each of these traces vary all the way from about 40 to all the way 200 million here. And I'm comparing the races raised by SHP versus HB. FHB is a naive ordering algorithm. RV-predict is a SAT-solving solver. And the races that I report here are essentially the pair of program locations for which there are events in race. And warnings are, so when you run a vector clock algorithm, it reports warnings as it sees events, and that's the number there. So as you can see, when you compare HB and SHB, HB reports almost double so if you sum up, the number is almost double that of SHB. So we manually inspected most of those, and all of those were false races. Let's look at how SHB compares with FHB. FHB is also sound, but it turns out that it misses a lot of races. So specifically look at these examples where it misses half of the races. RV-predict, the SAT-solving approach, on the other hand, does not do well. It does not scale, and the result of that is that they resort to windowing and miss a lot of races. If you look at warnings, all the warnings that SHB and FHB give are sound, but HB gives lots of spurious warnings. And as you can see, if a programmer is to use this tool, a tool that's based on HB, he's definitely going to frustrate if he's going to see 750,000 warnings. So let's look at some of the common patterns that we observed in our experiments. So this was one of the most common patterns wherein you write to an event, to a memory location X in some thread T1, and then later on in some other thread T2, you read from X, and then later on in the same thread, you read X again. Now, HB reports the first and the last event as races, but these are not really races. On the other hand, we also saw these other kinds of patterns, wherein you write to X, and then some other thread, you write to X again, and then you read it from X. Now, this naive approach of force ordering so that your sound does not detect the race between the write X and the read X in the last. And SHB, on the other hand, does detect that race. So in the interest of time, I think I should just conclude here by saying that SHB and HB are pretty competitive in terms of time. So to conclude, race detection based on HB can be unsound if you abuse the soundness guarantee of HB. We propose this other partial order called SHB, which is sound, complete, efficient, as well as is easy to incorporate. Experimental evaluation shows that it's a good approach. And in the future, we'd like to incorporate some more information for enhanced prediction, like control flow or data flow. And we'd like to see if other partial orders like CP and WCP are also amenable to such an analysis. Thank you.
Thank you, Mike. Do we have questions?
So I wonder about how your work compares to a very related work. So the aim is similar to come up with a sound data race detection, and they do this by maximal causality analysis.
So that is what is RV-predict out there.
Yeah, so what is the improvement here in addition to?
RV-predict essentially relies on SAT solving. So theoretically, it's even better than HB. HB can miss races that RV-predict can catch. But when you really go ahead and implement such an algorithm, you will have to do something for scalability. And if you ensure those things, you will end up missing races. That's the conclusion.
I see. So if I understand correctly, how you get given the trace, how you reason about the reorderings is more efficient.
Yes. So that also means that our reasoning is not very comprehensive. RV-predict can reason about a lot of other reorderings, but we don't. But we wanted to ensure that everything is linear time.
I see. Thanks.
Thank you.
Thank you. I was hoping that you could go back a few slides to this example of patterns that you've detected that are not races or not double, just not sound. So I still don't quite understand why you consider only one race on the left-hand side to be true and the other one not. I mean, after all, there is no synchronization, so there is no happens before relationship between two different threads, so the reads can be reordered in any way the compiler sees fit. So each read can see that right? So I don't quite understand.
First of all, we're assuming sequential consistency.
Sorry?
First of all, we're assuming sequential consistency. And this. Okay.
If you assume sequential consistency,
Yes.
then it makes sense.
Okay.
I thought it's Java, the relaxed Java method, which a lot of these will make no sense.
Okay, in the interest of time, let's thank Umang again. And next.